All right. I plan on spending a while in section 6.2. It's a very dense section. Today I'm going to focus on a specific type of cross-section, but I want to first show you that when we deal with volume in single variable calculus, where we have only one variable input and we're dealing with functions with only one variable output, we can't find just any volume. We have to find volume by adding up a bunch of areas. So what you want to realize is you're going to have cross sections perpendicular to, in this situation, in this picture, the perpendicular to the x-axis. There just has to be some formula for the area of that cross section. And then you see the thickness of the cross section like a loaf of bread. And you can see the idea of adding up a bunch of these little volume slivers. I like to call them slivers of volume because we're cutting the x-axis up into more and more and more pieces. And then we're letting the integral add all of these together. The bottom line for everything we do in area are these two formulas. We are either looking at a formula based on the x variable or a formula based on the y variable. The integrand is always going to start off with an area formula. Now, I've seen free response problems on the AP exam where they literally have given the area formula, and it was confusing to people because they expected to actually have to come up with something. What was I about to say? We typically use the letters A and B for the upper and lower bounds, and C and D for the upper and lower bounds of Y. That way to, hold on, focus. Okay. We typically use the letters A and B to look at an X interval, C and D to look at a Y interval. And we have to be very, very careful when we deal with respect to Y because we are so used to dealing with respect to X. Today we are going to do rotational volume. And I have found a variety of things on the internet. Here's one thing. Basically, you have some f of x function from A to B, and you're looking at the region between that function and the x-axis and rotating that whole region around the x-axis. And it creates a bunch of disks. And the disks are basically, where'd my pen go? They are cylinders. And there are some better pictures of cylinders to come, where the thickness or the height of the cylinder is your delta x. And then the area of the face is a circle. And what's the area formula of a circle? Pi r squared. But what you're going to see is you need to find a formula for the radius. And we're going to start off with easy, and we're going to slowly get into harder and harder versions of rotational area. But it starts off with just basically, you need to find a function for the radius, square it, and multiply it by pi. So let's go into an example. Now, I want you to know if your homework asks you to illustrate by sketching the volume, you do not have to do that. I have found people spend way too long trying to sketch something three-dimensionally, and your focus is really more on what is being rotated. So what you need to do is, one, identify the region they're describing. Sometimes that's not worded fantastically, just know that. The AP test, though, is excessively clear. So this is saying the region under the curve y equals root x from 0 to 1. And so that's including the x-axis as a boundary. You've got your region and then your axis of rotation. So what I do is I draw my xy plane, I draw the region, I identify the axis of rotation, and then one of the first things that I need to do is figure out whether I'm dealing with a dx or a dy situation, because you're in one or the other all the time. As you look at the picture that I've got highlighted, and then the picture right next to it, which is showing you what it visually looks like when you rotate the region in blue, and then in pinkish color, one of the discs. Now, because the width, the thickness of this disc is horizontal, that means it's a dx integral. When your cross sections are perpendicular to the x-axis, you are dealing with a dx integral. So we start off with knowing that it's with respect to x. Then I want to make sure that I'm using the x coordinates of the region. And those are my lower and upper bounds. Once that's settled, all that is left is the area formula. But you want to start off with the geometry of the area formula before you move into what's going on the xy plane. So despite the xy plane, if we're creating a bunch of these circular disks, the area formula for a face of the circular disk is pi r squared. Write that down first. And when I write my integrals like this, I like to call it the skeleton, the framework for the disk method. And then my last job is to figure out what the formula is for the radius with respect to x as I look at the two-dimensional drawing. And so perpendicular to the, perpendicular to the axis of rotation is your radius. And that radius is formed by subtracting two y coordinates, your y top and your y bottom. Now, you don't have to write -0. I'm going to write -0 to overemphasize the formula going on. So y top is y equals root x minus y bottom is just y equals 0. Your job from there is to simplify and solve the integral. So I'm not going to go over all of the integrations with you. I'll just do this one because it's quick. And if you have struggles with the integration, I can make a video for those examples that you need to see. So I've got my constant multiple pi, the square root of x is being squared. So I end up with one of the most simple integrals. And do a little, yay, I'm integrating. And then I put in the 1. And then I put in the 0. And I get pi over 2. And so that's what you're going to be doing. And the first several problems are supposed to be completely done without a calculator, just so you know. There are calculator problems on the homework later on. And you need to make sure that you know both how to use a calculator and how to figure things out without a calculator. So here comes another example. When you get a rotational volume problem, figure out what is the region being rotated. The region is bounded by y equals x cubed, y equals 8, and x equals 0. And we are rotating about the y-axis. And you can see a nice little picture with a sample disk. Now this time, do you see that the disk is giving the thickness as a vertical thickness, and it's a dy integral? So when I go to set the integral up, I start off with, this is dy. I need to know the upper and lower limits based on y of this region. So that would be y equals 0 to y equals 8. And once I have the limits and the differential, all my focus goes into area. I know I need an area formula with respect to y. I know that the geometry of this face of the disk is the area formula of a circle. So pi r squared. And then the very last thing is to actually go onto that xy plane and look at the specific functions involved. And see that your radius is this horizontal length. That means you need x right minus x left. But if you are given y equals x cubed, this is what gets people. You have to realize that if you need the right x coordinate, you need to know what x is equal to with respect to y. So you have to make sure to take y equals x cubed, cube root both sides, and see the function that you're actually dealing with from that perspective. The left x value is x equals 0. So you do the x on the right minus the x on the left. And again, you do not have to write the minus 0. I'm overemphasizing the formula. And then you've got it. Now it's just a matter of simplify a touch. So like bring the pi outside to make life easier. Change this to y to the 2/3 power dy, and you're ready for integration. Power rule it out, and then you've got an answer. Is this exciting? I think it's fun, but I'm also a math teacher, so. All right, next example. This time the region is enclosed by the curves y equals x and y equals x squared. And we are rotating about the x-axis again. Now, if you draw the curve that is between y equals x and y equals x squared, you'll see that we've got a different situation this time. if I am rotating what is in between these two functions about the x-axis, and it's like I'm holding it rigid and rotating it around, I'm getting a solid that has a hole in the middle. So what I have to do is I have to find the volume of the outer solid, but subtract from that the volume of the inner solid. And this is what they call the washer method. So the typical words that are used are disk method and washer method. And when you hear the word washer, what comes to mind? Yeah, I'm trying to grab you a lovely picture of a washer. Hey, hello, I'm a washer, not the washing machine, this one. So that's where the word comes from, and you can see why. And I don't know if you believe me on this one, but I would say about 15 years ago or so, I still am baffled by it. I had an entire calculus class and not a single person knew what a washer was. It was like it reached the high point of um, shop classes being looked at as non-academic and worthless. Seriously, that was the peak of that. Was we got a bunch of students taking calculus and thus going on into engineering and don't even know what builds things. And so that's when our robotics team saved the metal shop and things like that. Luckily, our school got smart before tearing down all of our industrial arts, because a lot of schools did. Anyway, so this time when you are focused on the area formula, you need to find, come on, pen. You need to find the area based on the big radius and subtract from that an area based on the inner radius. So we've got an outer radius and an inner radius. And we're going to have to look at the radius from 4 different points of view. What I mean by that is if I look to the right, then I can see that the function furthest from the axis of rotation is further right. The function closer to the axis of rotation is further left. And so I'm trying to still speak on a Friday, and I'm just watching the clock go down, you know. Now, if I am instead looking from the center left, then the function on the right is actually the one that is closer. The function on the left is actually the one that is farther. So you've got to draw the picture to see what is creating the outer radius versus what is creating the inner radius. And then we're also going to deal with looking up with outer and inner and looking down with outer and inner. So let's do this problem. Once you have the region drawn and you have identified the axis of rotation, you are ready to set up the differential. Is this dx or dy? Dx. Because my radius my radii are perpendicular to the axis of rotation. That means I need to focus on the x coordinates where the region exists, and that needs to be my lower and my upper bound. And now I focus on the area formula. First, the geometry formula. And I'm going to erase this so I've got room. The geometry formula is pi times a big radius squared minus pi times an inner radius squared. And this is the skeleton of the washer method. I want to get through this entire skeleton before I really worry about the specifics of what function subtracts from who and all that. So let me get some of this out of the picture. And this is what I tell people to do. Both radii are attached to the axis of rotation. So start on the axis of rotation. Then draw a line segment perpendicular to the axis of rotation heading toward the region. The outer radius will cut into the region, go inside the region, and reach to the outer edge, to the function who is furthest away. And label that with like a capital R. Then from the axis of rotation again, come out perpendicular toward the region, but stop when you reach the edge where the region is going to begin. The inner radius doesn't go inside of the region that is being rotated. It goes to the closest of the two functions to the axis of rotation. So now I label that with a little r, and I am ready to set up the rest of my integrand. I want to identify that these are vertical distances. Vertical distances mean I need to know the y top and the y bottom. So for my outer radius, y top is y equals x. The bottom y value is 0, which again, you don't have to write. The inner radius, the top y is x squared, and the bottom y is 0. It is completely set up. From there, it's just a matter of simplifying correctly and integrating correctly. And when you do your homework over the weekend, know that the most important thing to focus your time on is these integral setups. But also, I expect you to solve these integrals by hand as well until you hit the calculator section, and it's got the little calculator symbol. All right, ready for another one? Next. So we have a region bounded by the cube root of x and y equals x divided by 4 in the first quadrant and rotating it about the y-axis. Know that you're expected to draw this on your own without seeing the picture yet. So before seeing the picture, cube root of x, wee, wee. The line y equals x divided by 4. Well, yeah. So. But it also said lies in the first quadrant, so that's going to be this section. you are going to need to find the intersection points without a calculator. So you're going to do that using algebra. And in this situation, I can set equal to each other the cube root of x and x over 4. And then it's an algebra fun time. Cube both sides. And when you notice you have a polynomial, set one side equal to 0. Factor. And if it bothers you, you can multiply both sides by 64 if you don't like fractions. But hopefully you can look at that equation and see the solutions are 0 and plus or minus 8. Those are the x values. And even though we're focused in quadrant 1, we understand that there is an intersection point out here, but we're not going to use it. Now, this one is rotating about the y-axis. Because it's rotating about the y-axis, I have radii coming out perpendicular to that axis, and then that means this is a dy integral because it's the y-axis being cut up into small pieces. That means that when I get ready to set the integral up, I need to know the y values of the intersection, and I just found the x values. So plug 8 into either of them and see that you get y equals 2. So now I'm going to go over to the better drawing, the computer-generated drawing. And you can see understand that this is the only picture you actually need to get this whole thing set up. Not that the other pictures aren't worthy, they're very valuable, but you don't have to sit there and try to draw them unless you want to. But if you take a nice look at it, I've got a nice variety of pictures to think about all that's going on. What you're going to do is you're going to focus on, we set up an integral with respect to y from 0 to 2. And when I draw my radii, I'm going to start at the axis of rotation, draw perpendicular to the axis of rotation, through the region to the furthest function from the axis of rotation, and label that capital R. The inner radius from the axis of rotation, come out perpendicular to the axis of rotation, and stop before you go in the region to the closer of the two functions for the little r. Then you recognize that you have an area situation of pi times the outer radius squared minus pi times the inner radius squared. But now is the time to focus. You need to know a horizontal distance. You need to know an x on the right and an x on the left for both of these. That means you need to solve for x in terms of y. Now, the red function is y equals the cube root of x. the blue function, y equals x divided by 4, you need to change the variable. Cube both sides. Yeah. And you get x equals y cubed. Multiply both sides by 4, and you get x equals 4y. And that particular step is the one people tend to accidentally miss. And you can see right here, so always take a moment to ask yourself, am I dealing with a horizontal distance for radius or a vertical distance for radius? If it's vertical, then I'm subtracting y's. If it's horizontal, then I'm subtracting x's, and I need to know what x is equal to. Then, time to fill in the radii. So for the outer radius, the capital R, the right x is 4y, minus the left x is 0. For the inner radius, the right x is y cubed, the left x is 0. That looks like a G, and it's bugging me. There we go. From there, you'll make the algebra look nicer, use some power rule, and enjoy the integration. Are you ready for another one? Are you ready for another one? Yay! Yay! Here comes another one. Yeah. Region bounded by these two graphs, but this time it's going to rotate about y equals 4. And I want to emphasize again to you that you need to be able to draw these graphs by hand and find their intersections by hand. So I've got my y equals x. And then for x squared minus 2x, leading coefficient positive, a right side up parabola goes through the origin and through 2. Whee! I need to know the intersection points so I can set the two functions equal to each other. And get that it exists between x equals 0 and 3. And I've got to say, if you look at this region, you are hoping that they do not ask you to rotate about the y-axis. Think about how awful that is. But it's for that reason that there's another technique that the AP test doesn't cover. So sadly, I've stopped teaching it. What? Okay. Yeah, thank you guys for being on chat. I was not paying attention to it. I appreciate it when you help each other. Okay, so I'm now going to look at the computer drawn version. And again, rotating about y equals 4. So I'm going to draw my radii. My radii are attached to the axis of rotation. The outer radius comes from drawing perpendicular toward the region, through the region to the furthest function. And then my inner radius from the axis of rotation, go perpendicular to it toward the region, but stop at the edge before you enter for the smaller inner radius. Then identify, is this a dx or a dy situation? Dink. This one is dx, and because what you want to see is these radii coming out perpendicular to a horizontal axis when they are rotating around. It's actually a horizontal cut that makes it a sliver. And one of the things you can depend on is if the radius is perpendicular to the x-axis, it's a dx. If the radius is perpendicular to the y-axis, it's a dy. So I get it ready, dx, and the x coordinates are between 0 and 3. And then I'm stop for a moment and think geometry. Not the functions here, who's the radius, doesn't matter, geometry. Yes, anytime you rotate over the x-axis, it's a dx. Anytime you rotate over an axis parallel to the x-axis, it's dx. And you want to see visually why that is creating dx, because if the radii are vertical, they're taking up a vertical length. As we create volume, we don't want to double use one of the variables. And so we don't want to use y if we are already using it for a specific radius. We need another dimension for the tiny cuts that take us into the volume dimension. Then geometry. You're dealing with the area of a big circle or an outer circle minus an inner circle. And it's not until this point that it really matters to focus on who these are. Now, these radii are vertical. So that means you have some top y value minus some bottom y value. For the outer radius, the top y value is 4. The bottom y value is x squared minus 2x. And don't forget that parentheses. For the inner radius, the top y value is also 4. The bottom y value of the inner radius, though, is x. At that point, integral setup is done. It's just a matter of not messing up your subtractions and your multiplication and addition. That's where it tends to go wrong. So just always slow down for those things. Write as much as you need to be accurate. And then if you want, you can come back and watch the video and look at these pictures. I can also tell you some websites to go to see other people's way of looking at it, because we've got a lot of technology out there now to show you more visually. Alrighty. I think this was the last one, last example. This time the region is bounded by these two functions. And again, I expect you to be able to draw these by hand. So you should recognize the square root function, stretched a little bit, and then moved right 1 unit. I'm trying to draw it stretched. Then the other one, y equals x minus 1. I need to find the intersection points. So I'm going to set them equal. And I'm going to square both sides. Have some fun. Distribution property. Whoops. Set one side equal to 0. Factor. And I'm getting that they intersect at x equals 1 and at x equals 5. Also know that if you had solved this equation in a slightly different way, no, never mind. No, let me not go there. All right, let's look at the region. We are rotating about a vertical line, x equals -1. Now that vertical line is parallel to the y-axis. Right, dy. It would be dy. And you'll want to find your way of what clicks for you. What I typically tell people is when you're using the disk method, your radius comes out perpendicular to the axis of rotation. And if you are coming out perpendicular to the y-axis, it's a dy. If you're coming out perpendicular to the x-axis, it's dx. So you'll want to find your way of figuring that out. But any vertical axis of rotation, it's a dy. Any horizontal axis of rotation, it's a dx. So you can also see it better sometimes when you draw the radii. When I do draw the radii, I will go from the axis of rotation perpendicular toward the region. My outer radius goes inside the region to the furthest of the two functions. My inner radius from the axis of rotation perpendicular toward the region, but stop when I reach the closest function without going inside the region. When you look at those and you try to picture those rotating about the y-axis, you want to picture these washers with a tiny dy, a tiny vertical for the cuts. So if you can picture a bunch of layers of these discs on top of each other, you can see the vertical cuts. And there are some videos I can send you to watch to help you see this better as well. So I'm starting off with, it's a dy integral. I need to know the y coordinates of intersection. And I had found the x, so I need to go back and, based on x equals 5, find that it is y equals 4. So bottom y of the region is 0, top y of the region is 4. Now it's all about the integrand, and I know I need an area formula with respect to y. I know the area formula that I'm going to use is area of a circle, pi r squared, minus area of an inner circle, pi times inner radius squared. I want to take a moment to recognize that these distances are horizontal. I need to know my right x and my left x. So then I look at my outer radius, its right x coordinate I have to change this equation and write it as x equals y plus 1. And then minus my left x is negative 1. You guys will probably end up just writing plus 1. Then for my inner radius, I need to know the right x coordinate, which means I'm going to have to again, and this shows it right there. I've got to take the equation that's that has y isolated and instead isolate the x. So on my inner radius, the right x is following y squared over 4 plus 1 minus the left x is negative 1. And then it's all set up, ready to go. Now, there are a lot of nice animations out there that can help you with this. And there's so much out there. It's a matter of what speaks to you. So I found a few things. This one actually looks pretty good if you're having any struggles. I think this one's really nice too. I found it while I was, the person talks through it. Because we don't have a lot of time, I'm just going to kind of fast forward. And let me mute it because... Okay. Where's the mute? Or I don't know. Anyway, I'll leave a link for this, but it's really nice because it goes through and shows the animation and it moves it around to help you see it a little bit better. But I'm looking at the fact that I have less than 2 minutes and I can't really show you all this, especially when I've got lag time. Oy. But anyway, I'll leave a link for that. Ooh, there you go. Ooh, isn't that pretty?
That's exactly the right idea. The thinner the discs get, the the better they approximate the actual volume of this solid. Let's get into the math behind the idea. We'll first find the volume of a single disk. But remember, the disks get crazy thin. Let's call the height dx because it's located along the x-axis, and to indicate how incredibly small it will become. The radius of this disk is simply y, the vertical distance from the x-axis to the graph. But y is equal to x squared. So an equivalent way to write the radius is just x squared. This is ideal because now our variables are all both in terms of x. In case you don't remember, the volume of a disk is of x only.
Oh, that was the wrong pause.
The volume of one disk in complete generality.
Okay, now I'm trying to stop because our time is up.
We're able to write down a formula for this.
Shh, quiet. Okay, so another thing that I found was a nice little Desmos where you can push play. Let me show you this. It's really cool. So you can see it being created. You can change the function. You can change the starting and the end point. So there are a lot of things out there that you can play with to help you out. And I'll put some links up, and you can even find your own stuff too. But it is time to go to lunch. So I will see you tomorrow. No, it's Friday. Woo! I will see you Monday.